Now we will understand quantum numbers. To obtain the complete information of all the electrons present in atom, we need a set of 4 numbers that is said to be quantum numbers. Quantum numbers are 4. Principal quantum number, which is denoted as small n. Second, azimuthal quantum number, which is denoted as small n. Third, magnetic quantum number, which is denoted as ml. And fourth quantum number is spin quantum number, which is denoted as ms, spin of electron. So there are 4 quantum numbers: principal quantum number n, azimuthal quantum number l, magnetic quantum number ml, and spin quantum number ms, that is spin of electron. First we understand about principal quantum number is denoted as n and it was given by Bohr. Principal quantum number represents name, size, and energy of cell. Its values are from 1, 2, 3, 4, etc. And 1 is designated as capital K, 2 as L, 3 as M, 4 as N, etc. So we can write the cells are K, L, M and N. Now, as we know the formula for radius is equal to A0 n square by Z, where A0 is equal to 52.9 picometer into n square by Z. So we can say as value of principal quantum number n increases, distance from nucleus also increases. Therefore we can write R1 smaller R2 smaller R3 and so on. Energy of electron is given by the formula En is equal to minus 13.6 upon n square into Z square electron volt per atom. From this we can say as n increase, energy also increase. As n increase, energy also increase. Means we can write E1 smaller E2 smaller E3 and so on. Now for the formula, velocity is equal to 2.18 into 10 raised to 6 Z upon n meter per second. the formula for velocity is 2.18 into 10 raised to 6 into z upon n meter per second. From this formula we can say as n increase, velocity decrease. Means we can write V1 greater than V2 greater than V3 and so on. Now, angular momentum. Angular momentum mvr is equal to nh upon 2 pi. Here n is principal quantum number. N is principal quantum number. Now, we can find out the total number of electrons. Total number of electrons by using formula 2n square. Say n is equal to 1. If n is equal to 1, then total number of electrons are 2 into 1 square, that is 2. Total number of electrons is equal to 2. N is equal to 2. N is equal to 2. Then total number of electrons 2 into 2 square, that is 8. For n is equal to 3. For n is equal to 3, 2 into 3 square, that is 18. And for n is equal to 4, 2 into 4 square, that is 32. So we can say that in cell K, total number of electrons are 2. In L, total number of electrons are 8. In cell M, total number of electrons are 18. And in cell N, total number of electrons are 32. Now we understand azimuthal quantum number. Azimuthal quantum number. Azimuthal quantum number is denoted as a small n and it was given by Sommerfeld. It was given by Sommerfeld. Value of L represents subcell and orbital angular momentum. Orbital angular momentum. Value of L represents subcell and orbital angular momentum. Means we can say azimuthal quantum number represent subcell and orbital angular momentum. Now, azimuthal quantum number has different names like subsidiary quantum number or secondary quantum number also. So now we are going to understand more in detail about azimuthal quantum number. If value of n is equal to 1, that is principal quantum number value n is equal to 1, then value of L is equal to 0 because value of L is equal to 0 to n minus 1. Value of L is equal to 0 to n minus 1. So if n is equal to 1, we get L is equal to 0. If n is equal to 2, then L is equal to 0 and 1. If n is equal to 3, then value of L is equal to 0, 1 and 2. And if value of n is equal to 4, that is principal quantum number n is equal to 4, then L values are 0, 1, 2 and 3. Now, L value 0, 1, 2, 3, 4 or 5, then it represents the name of the subcell, say S, P, D, F, G, H, etc. So from the value of L, we can get the knowledge of this subcell S, P, D, F, G, H, etc. Now we study that n is equal to 1, L is equal to 0. Means if principal quantum number is 1, then subcell is also 1. So for n is equal to 1, subcell is also 1. For n is equal to 2, subcell 2. For n is equal to 2, we can say subcells are 2. For n is equal to 3, subcells are 3. And for n is equal to 4, subcells are also 4. Now, angular moment, that is orbital angular momentum, orbital angular momentum is given by the formula square root L plus 1 and outside the square root h upon 2 pi, or we can write square root L plus 1 h bar, where h bar is equal to h upon 2 pi is also called Hess. Now again, orbital angular momentum is given by the formula L plus 1 h bar, or L plus 1 h upon 2 pi. So first we find orbital angular momentum for s orbital, 1s orbital or 2s orbital or for 3s orbital. Because we can say that orbital angular momentum depends on the value of L. Here S is given, therefore L is equal to 0 as I mentioned. So orbital angular momentum for any s orbital will be L plus 1 h upon 2 pi. So we will get as S for S, L value is equal to 0. So we will get 0 into 0 plus 1 h upon 2 pi. So answer will be 0. So orbital angular momentum for S orbital, orbital angular momentum for S orbital is 0, whether it is 1s, 2s or 3s or 4s. Same way for P orbital, say it is 2p, 3p, 4p, any P orbital, orbital angular momentum is equal to root L plus 1 h upon 2 pi. But as L is equal to 0, 1, 2, 3, we have S, P, D and F. So P, as P orbital is present, we can take L value to be 1. So orbital angular momentum of P orbital orbital angular momentum of P orbital is equal to root 2 into h upon 2 pi. Now we have studied total number of electrons in particular subcell is given by the formula. Total number of electrons in particular subcell is equal to 2 in the bracket 2L plus 1. So for S subcell, total number of electrons is equal to, when keeping value of L is equal to 0, we will get 2. That is why S subcell will contain maximum total number of electrons is equal to 2. P subcell, total number of electrons is equal to 6, because L is equal to 1, we will get 3 into 2, that is total 6 electrons. Same way, D subcell, total number of electrons is equal to 10. Keeping value L is equal to 2, we will get 10 electrons. Same way, F subcell, total number of electrons is equal to 14. So we can say S 2 electrons, P 6 electrons, D total 10 electrons, and F 14 electrons. S spherical, P is equal to, shape of P subcell is dumbbell, shape of D subcell is double dumbbell. But for dz square, orbital dz square, the shape is not double dumbbell. For F, it is complex. Also we have to remember that S is sharp, P is principal, D diffused, and F is fundamental. This terminology were utilized for the spectral lines previously. Now we will understand about magnetic quantum number. Magnetic quantum number. Magnetic quantum number is denoted as M or Ml, and it was given by Linde, and it represents total number of orbital present in particular subcell. Its values are minus L2 plus L, means all integer, minus L2 plus L, including 0. So, total number of ml values is equal to 2L plus 1. Total number of ml values is equal to 2L plus 1. 2L plus 1. Now, if L is equal to 0, L is equal to 0, then ml value is also 0 and the type of orbital is s orbital. Type of orbital is s orbital. So maximum number of electron is equal to 2. Maximum number of electrons is equal to 2 for s orbital. Now if L is equal to 1, then ml value is equal to -1, 0 and plus 1. L is equal to 1, then ml is equal to -1, 0 and plus 1. And that is p orbital. P orbital. P orbitals are of three types: px, py and pz. And ml value for pz is 0 and for px and py we can take plus or minus 1. So if L is equal to 1, then ml values are -1, 0 and plus 1 and we get total number of electrons is equal to 6. Now, L is equal to 2. L is equal to 2. Then ml values is equal to 2L plus 1. So 2 into 2 plus 1, that is 5. Total ml values is equal to 5. They are -2, -1, 0, plus 1 and plus 2. And we have d orbitals. L is equal to 2 means d. So we have dxy, dyz, dz square, dxy, dyz, dz square, dxz and dx square minus y square. dxy, dyz, dz square, dxz and dx square minus y square. So total orbitals of d type are 5. Now if L is equal to 3, then ml values 2L plus 1. So total ml values will be 7 and they are -3, -2, -1, 0, plus 1, plus 2 and plus 3. -3, -2, -1, 0, plus 1, plus 2 and plus 3. And these are 7 f-type orbitals. So from the knowledge of magnetic quantum number ml, we can get the knowledge related to total number of orbitals. Now, principal quantum number is n. Principal quantum number is n. Second quantum number is azimuthal quantum number. Which is denoted by small n, and third quantum number is magnetic quantum number, which is denoted as ml. So starting from n is equal to 1, principal quantum number n is equal to 1, azimuthal quantum number L is equal to 0. So ml is also 0. Now for n is equal to 2, we will get L is equal to 0 and 1. So ml values 0 and ml values -1, 0 and +1. So here we can say only S subcell. Here S and for this it is P subcell. S and P both the subcell. Means principal quantum number 2 we get S subcell as well as P subcell. If n is equal to 3, then L is equal to 0, 1 and 2. Therefore, ml values 0 or +1, 0, -1, simply -1, 0, +1, and ml value from 2, -2, -1, 0, +1 and +2. So here we can say S subcell, here P subcell. So we can say S type of orbital only 1, P type of orbital 3, and D type of, we can say D type of orbital 5. Now n is equal to 4. N is equal to 4. Values of L 0, 1, 2 and 3. So ml values 0. From 0 ml is equal to 0. If L is 1, then ml is equal to -1, 0, +1. For 2, ml is equal to -2, -1, 0, +1, +2. And for 3, ml is equal to -3, -2, -1, 0, +1, +2 and +3. So here again we say this is for S, this is for P, D and this is for F. So simply we can understand about principal quantum number, azimuthal quantum number and magnetic quantum number by this table formation. We will understand spin quantum number. Spin quantum number is denoted as ms. As we know that electron revolves around the nucleus, same way it spins on its own axis, and that is why we have to understand about the spin quantum number. It was given by Uhlenbeck and Gauss-Schmidt. Now, electron spin is possible in two ways, clockwise and anti-clockwise. So we can draw clockwise rotation this way and another anti-clockwise rotation this way. So if clockwise, generally it is designated as +half, and if it is anti-clockwise, then it is designated as -half. So from this knowledge of spin quantum number, we can say that any orbital contain maximum 2 electrons with opposite spin. And that can be given by just drawing orbital in which we have 2 electrons with opposite spin. So this is correct way. But if we write then this is wrong way. So from the knowledge of spin quantum number, we can get the idea that any orbital can contain maximum 2 electrons. Now, spin angular momentum, is given by the formula S plus 1 h upon 2 pi or S plus 1 h bar. We will understand shapes of orbitals. First we understand the definition of orbital. What is an orbital? The three-dimensional space around the nucleus in which the probability of finding electron is maximum is known as orbital. And we have total 4 types of orbital: S, P, D, F. Also we have G, H, etc. Now we also understand one more term, that is node. Node is nothing but it is a point or line or plane or surface where probability of finding electron is 0, is said to be node. Total number of nodes is equal to n minus 1. Now, radial nodes or spherical nodes is found out by using formula n minus L minus 1. And beside with these radial nodes, angular node is equal to simply say L. So this is about node. Now we will understand the shapes of different orbitals like S, P, D. S orbital. S is spherical. It means to find out the electron around the nucleus is same at all distances. We have different type of S orbitals like 1s orbital, 2s orbital, 3s orbital, etc. If we draw the boundary diagram for S orbital like 1s, then simply we can draw this is 1s orbital in which there is no node. It means we can say we don't find any region where the probability of finding electron is 0. And for 1s orbital we can say that probability of finding electron is maximum around nucleus and it decreases as we move away from the nucleus. So this is about 1s. So there is no node present in 1s orbital. But if we want to draw the boundary diagram of 2s orbital, then this region is considered as nodal plane or node. So we can say that 2s orbital has one node. 2s orbital has one node. Again we can say for 2s orbital that probability of finding electron for 2s is also maximum near the nucleus, and it decreases to 0 as we move away from the nucleus. But in the intermediate region we find one node. So the difference between 1s orbital and 2s orbital, that 1s orbital principal quantum number n is equal to 1, but for 2s principal quantum number is equal to 2. In 1s there is no node present, and in 2s there is one node present. And energy is concerned and size is concerned, we can write 1s smaller 2s smaller 3s and so on. So energy and size of 1s orbital is smaller than 2s. Size of and energy of 2s orbital is less than 3s. So this is about s orbital. Now we will understand for p orbital. We will understand the shape of p orbital. When n is equal to 2, principal quantum number n is equal to 2, we have L value 0 and 1. So value of L is equal to 1, that is we get ML values -1, 0 and +1. And these are three orbitals of P, Pz, Px and Py. So Px and Py can have plus or minus 1 values, and Pz, ML value for Pz is equal to 0. Now we can say that there are three types of p orbital. P orbitals are of three types. They are equal in energy but different in direction and charge distribution. So if we want to draw the diagram, boundary diagram of p orbitals, we can draw Px, Py and Pz. When we draw Px orbital, then this is the boundary diagram for Px orbital. Same way, this is boundary diagram for Py orbital, and this is the boundary diagram for pz orbital. Px, Py and Pz are situated perpendicular to each other. Also we have to remember that in Px, Py or Pz, these are said to be lobes. In any diagram, we can consider this portion or this region to be lobe, or simply we can say LOBE, lobe. Now, where the two lobes meet each other, that point is said to be node. This point is said to be node. It means the finding electron, probability to find electron is 0 near node. Now, there are nodal planes in Px, Py and Pz. There are nodal planes present in Px, Py and Pz. For Px, nodal plane is Yz. For Py, nodal plane is Xz, and for Pz, nodal plane is XY. Now, nodal surface of npx orbital is given by the formula n-2. Nodal surface for npx is given by the formula n-2. We understand the shape of d orbital. When ml values are -2, -1, 0, +1 and +2, then total 5D type of orbital are possible. So D are 5 types of orbital equi-energy, and they are dxy, dyz, dz square, dxz and dx square minus y square. Once more, total d orbitals are 5: dxy, dyz, dz square, dxz and dx square minus y square. ml value for dz square is 0, and here it is -2, -1, +2 and +1. Now, shapes of d orbital. D orbital is double dumbbell, shape, but dz square has no the double dumbbell shape. It has a shape of baby suthar. Now we study different d orbitals, shapes of different d orbitals. First we understand dxy, orbital dxy. when we draw a simple diagram taking x here and y here, we can draw this is a double dumbbell shape of dxy orbital. Same way dyz orbital. Taking x here and z here, this is the shape of dyz orbital. Same way dxz orbital, x and z. Dy, if we here taken dyz, that is why y will come here. And now for dxz, so this will be the shape of dxz. Now dx square minus y square. Dx square minus y square. The shape of dx square minus y square is in this way, and we can see that dxy, dyz, dzx and dx square minus y square all are double dumbbell. They have 4 lobes. But in the case of dz square, as I told that it is a shape like baby shooter, we can draw dz square to be this is the shape of dz square orbital. So these are the shapes of d orbital. Now one more formula that is utilized to find out nodal surface of n dxy is equal to n minus 3. Nodal surface of n dxy is equal to n minus 3. Now f orbital, if ml values are minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3, then total number of f orbitals are 7. But their shape are complex. So we have studied the shapes of s orbital, p orbital, d orbital and f orbital. Given question, what is the total number of orbitals associated with principal quantum number n is equal to 3? Principal quantum number n is equal to 3, then azimuthal quantum number L values are 0, 1, 2, 0, 1 and 2. Therefore, magnetic quantum number ML values are, for L0 we have 0, for 1 we have minus 1, 0 and plus 1, and for 2 ML values are minus 2, minus 1, 0, plus 1 and plus 2. So for 0 we can say 1 orbital, for minus 1, 0 and plus 1 we have 3 orbital, and for minus 2, minus 1, 0, plus 1 and plus 2 we have 5 orbital. It means total 9 orbitals are present. We can say if principal quantum number n is equal to 3, then total number of orbitals associated are 9 orbitals. But the same answer can be found out alternatively by using the rule n square. Total number of orbitals is equal to n square. So we get 3 square is equal to 9. That is total number of orbitals. Now in the next question, describe the orbital using SPDF notations with n value 2, L value 1, n value 4, L is equal to 0, n is equal to 5, L is equal to 3, n is equal to 3, L is equal to 2. First of all, azimuthal quantum number value L, 0, 1, 2, 3, we can write the subcell S, P, D and F. Using this knowledge and the given information, for first one, n is equal to 2, L is equal to 0. So the orbital name is 2s, or simply we can say that it is 2s orbital. For B, n is equal to 4, L is equal to 0. First one is not 2s but it is 2p because L value is given 1. Therefore, it is 2p. Now for the second one, n is equal to 4, L is equal to 0. It is 4s orbital. For C, n is equal to 5 and L is equal to 3. Therefore, it is 5f orbital. And for last D, n is equal to 3, L is equal to 2. So we can say 3d orbital. So orbitals are 2p, 4s, 5f and 3d. Why the answer is 2p? Because principal quantum number is 2. So first we have to write principal quantum number and L value is equal to 1. So if L is equal to 1, then the subcell is p. That is why it is known as 2p. Same way in the second one, principal quantum number is 4 and L value is equal to 0. So L is 0, then it is S subcell. Therefore, second answer is 4s. First we have to write principal quantum number and second we have to write azimuthal quantum number. Same way for the third one, n is equal to 5 and L is equal to 3. Principal quantum number is 5 and from the table L value, if it is 3 given, therefore we can write F subcell means 5f. And for the last one, n is equal to 3, L is equal to 2. Therefore we can say it is 3, principal quantum number 3 and L is equal to 2. So we can say it is 3d orbital. In the given problem, write down the values of azimuthal quantum number possible for electron present in third cell. First of all, third cell means principal quantum number n is equal to 3. Principal quantum number n is equal to 3. So azimuthal quantum number L has value 0 to n minus 1. Therefore, if the third cell means principal quantum number n is equal to 3, then the values of azimuthal quantum number L is equal to 0, 1 and 2. Now in the next question, how many orbitals are present in p subcell? To find out orbitals present in cell, we can utilize the formula 2L plus 1 and L values 0, 1, 2, 3, we can write S, P, D and F. Subcell S, P, D and F. Here we are given P subcell means 2 into 1 plus 1. So we can say total number of orbitals present in P subcell is equal to 3. Now in the next problem, give the possible values of L, ML and MS for electrons having n is equal to 2. Principal quantum number n is equal to 2. So azimuthal quantum number L can have value 0 and 1. Therefore, ML values for L is equal to 0, ML is equal to 0. So MS is equal to plus or minus half. Spin quantum number plus or minus half. Now for L is equal to 1, L is equal to 1. We can write ML value to be minus 1, 0 and plus 1. So corresponding MS value we can write plus or minus half, again plus or minus half and here also plus and minus half. So we can write the possible values of L, ml and ms for electrons having n is equal to 2 in this way. Here in this problem, it is given that from the following set of quantum numbers, state which are possible. First we understand that total sets are given 4 in which n, l, ml and ms values are given. First we understand for set number 1 in which principal quantum number n is equal to 0, l is equal to 0, ml is equal to 1 and ms is equal to plus r. So we can say that this set is not possible because principal quantum number n always starts from 1, but here it is given n is equal to 0, and that is why we can say that this set is not possible because n starts from 1, 2, 3, etc. Now, in the second set, n is equal to 2, l is equal to 1, ml is equal to 0 and ms is equal to minus 1. For the second set, n is equal to 2, so value of azimuthal quantum number is 0 and 1, so here it is possible. Same way ml value is 0 and minus 1, 0 and plus 1. So here we have ml value also possible, and spin quantum number may be minus up or plus up. That is why we can say that set number 2 of quantum number is possible. Now for set number 3, n is equal to 2, l is equal to 0 and ml is equal to 3 is given. So for set 3, n is equal to 2. So L is equal to 0 and 1 and ml values 0, minus 1, 0 and plus 1. But here ml value is given 3. It means that this is not possible. This set is not possible. Because we can see the value of ml may be 0 or minus 1, 0 and plus 1. As it is given here ml is equal to 3, we can write that this set is not possible. Now for the fourth set, n is equal to 3. N is equal to 3. L is equal to 1. So for n is equal to 3, value of L 0, 1 and 2. So here it is possible. L value is also acceptable. Now ml value. ml value for 0 will be 0. For 1 it is minus 1, 0 and plus 1. And for 2 it is minus 2, minus 1, 0, plus 1 and plus 2. Since here it is given ml value 0, means we can say, and also ms value is given minus 1 half. ms value is given minus 1 half. Minus 1 half or plus 1 half, that is spin quantum number of electron may be minus 1 half or plus 1 half. Means we can say set 4 is also possible. This set is possible. Given question, we have to write down the quantum numbers n, l, ml for the following orbitals. The orbitals are given in this manner: 3d x square minus y square, 4d z square, 3d xy, 4d xz, 2pz and 3px. Before we study the answer, we must know that values, ml values for d orbital, there are 5 d orbitals: dxy, dyz, dz square, dxz and dx square minus y square. We can write down the value. We can write down the value of ml as minus 2, minus 1, 0, plus 1 and plus 2. but this value can be written as this way. It means that we can write dxy ml value for dxy minus 2 and plus 2 also. Same way for dx square minus y square, we can write plus 2 or minus 2. dyz and dzx minus 1 or plus 1. But for dz square, it is 0. Same way, for 3 orbitals of p, px, py and pz. Px, py and pz. For pz, ml value is 0. And for px, it is plus 1 or we can say minus 1, then plus 1 here. It means we can write for ml value for px or py, we can interchange minus 1 or plus 1. After getting knowledge regarding the ml values of d orbital and p orbital, we can assign the quantum numbers n, l and ml for these all orbitals. For the first case, n is equal to principal quantum number 3 and l. Again, L value 0, 1, 2 and 3 we write S, P, D and F. So here we have D subcell, so we can write it is 2. And ML value x square minus y square, either minus 2 or plus 2. Now for 4D z square, for 4D z square, n is equal to 4. Principal quantum number n is equal to 4, and as it is D subcell, we can again write it is 2. L is equal to 2. And for dz square, the value ml is 0. Now for the third orbital, 3dxy, principal quantum number n is equal to 3. For D subcell, we can write D is there, therefore it is 2. And dxy, either minus 2 or plus 2. Now for 4dxz, principal quantum number n is equal to 4. But for D subcell, again, L value is equal to 2. And dxz means we can write plus 1 or minus 1. ML value is plus 1 or minus 1. Now for 2pz, next orbital, that is 2pz. Principal quantum number n is equal to 2. Hence it is p given, subcell is p, we can write L value to be 1. And for pz, ML value is 0. Now for 3px, principal quantum number is equal to 3. Principal quantum number 3. Again for p orbital, L value is 1. And px, we can write ML value to be minus 1 or plus 1. So this way we can write n, L and ML values.